Module 3, Lecture B, Files and Errors. By the end of this lecture, you will be able to read text and CSV-style engineering data files using built-in file handling, write calculation results and simple reports to text files with clear formatting, and handle common runtime errors using exceptions and defensive checks. Reading data files. Opening data files. Opening a data file lets a program read stored engineering measurements, such as temperature, pressure, or vibration data, without changing the original file. To do this safely, the program needs the file's name, location, and format. This protects valuable data while making it available for analysis and responsible data management. When opening files, distinguish the file name from the file path. The name identifies the file, while the path tells the program where to find it. If the path is wrong, the file may not open, even if it exists. Consistent naming and folder organization are especially important in engineering projects, where many related files must work reliably across different computers. Opening a file uses system resources, so the connection must be managed carefully. After reading the data, close the file to tell the operating system the work is finished and to avoid problems such as file locks. Automatic closing features can help, but programs should still handle common issues like missing files, permission errors, wrong locations, or incompatible formats by checking the file, reading safely, and closing it when done. Python code. Opening data files. Create and open small engineering data files carefully, using a safe read mode when working with original records. Use context managers so files are closed automatically after use. We import path from the pathlib module to work with file system paths in a clear, object-oriented way. It helps create and manage paths that are readable and work across different operating systems. We create a path object with the pathlib module to represent the location of the temperature log file. This makes the code clearer and more portable across operating systems and gives us a convenient way to read from or write to the file later. This example writes a small set of sensor data to a text file using a path library method. The file contains column names followed by a few rows with time in seconds and temperature in Celsius. This creates a simple log dataset that can be read and processed later. The code first verifies that the path exists and points to a file, not a directory. It does this with the path object's exists method and isFile method. These checks help avoid errors before trying to open the file. The file is opened in read-only text mode using UTF-8 encoding, which lets the program safely read a wide range of characters without changing the file. A context manager is used so the file closes automatically when reading is finished, helping prevent resource leaks. The code reads the file's header line and removes extra white space so it is clean for use. It then reads the first data line and strips white space as well, making the entry ready for processing without unwanted characters. The code prints key details to confirm the file was opened and read correctly. It shows the file being processed, the read-only text mode, the header line, and the first line of data. Together, these checks verify that the file has the expected structure and contents. The else block handles the case where the expected file is missing. It informs the user that the file was not found and helps the program continue safely instead of crashing. If the file cannot be found, the program displays a message with the missing file location instead of crashing. This gives the user clear feedback about what went wrong. After the context manager finishes, The code checks whether the file has been closed by printing the file object's closed status. Because the file was opened with a context manager, it should close automatically when the block ends, supporting proper resource management. This script shows safe, basic file handling in Python using a small temperature log. It first creates sample data, checks that the file exists, then opens it in read-only mode with a context manager so it closes automatically. It reads a few lines and reports key details while handling a missing file without crashing. The example highlights careful checking, clean reading, and confirming that the file is closed afterward. Line reading. Line reading is an efficient way to process engineering data files because these files often store records one line at a time. Each line may represent a measurement, simulation step, or log entry, so reading line by line helps manage large files without using too much memory. It also lets programmers inspect, clean, convert, and use each record in calculations as part of a structured sequence. Text read from a file often needs cleaning before it can be used in calculations. Lines may include spaces, commas, labels, headers, or units, so the program must separate the useful parts and convert them into numbers. In engineering, correctly understanding the file format is essential because small parsing mistakes can cause failures or inaccurate results. Line reading improves data quality by letting you process files one line at a time and handle problems such as missing values, blank lines, or unexpected formats. This makes it easier to clean and transform real-world data reliably. It is especially important when accurate analysis depends on connecting a file's structure to the right processing steps. Python code, line reading. Process engineering data line by line, cleaning each text entry before converting it to numerical values. Ignore headers, empty lines, and records that are faulty or cannot be used. We begin by setting up a small sample sensor log stored in a CSV file named bridge strain log. This simulated data file provides the input needed to test the code that will process and analyze the sensor readings. The example uses a text string containing comma-separated engineering data with columns for time, strain, and temperature. Most rows contain valid measurements, while one row includes a missing value to represent a faulty record. This sampled data is meant to show how a program reads, cleans, and handles both valid and invalid entries. To write sample data safely, open the file in write mode with UTF-8 encoding, so special characters are handled correctly. Use a context manager to write the text, which ensures the file closes properly, even if an error occurs, helping prevent data corruption and resource leaks. The process begins by creating organized storage for the valid data. Separate lists hold time, strain, and temperature readings, while a counter tracks rows that are skipped because of errors or missing values. The bridge strain log CSV file is opened for reading with UTF-8 encoding, so special characters are handled correctly. The first line, usually the header, is read and trimmed of extra whitespace to prepare for processing the remaining data. The code processes the file line by line, skipping the header. Each remaining line is cleaned by removing extra whitespace at the beginning and end. This helps prevent spaces or new line characters from causing errors when the data is parsed. The code checks whether a line is empty, and if so, increases the skipped row count. It then moves directly to the next line, so empty lines are ignored, and only lines containing data are processed. The code splits a cleaned line of text at each comma to separate it into individual data fields. This makes values such as time, strain, and temperature easier to access and process correctly in later steps. The code checks each line to make sure it has the expected 3 columns. Lines with the wrong number of parts are skipped, and the skipped row count is increased. This keeps only correctly formatted lines for further processing. The code safely converts text entries into floating point numbers for time, strain, and temperature. It uses error handling so that if any conversion fails, the program catches the value error and continues instead of crashing. This code handles errors that occur when text values cannot be converted into numbers. If a conversion fails because the data is not numeric, the row is counted as skipped, and the loop moves on to the next line. This keeps invalid records out of the processed results, while allowing the file to continue being read. This code keeps only valid numerical records by adding each successfully converted value to its matching list. The time, strain, and temperature values are stored separately, so faulty or incomplete entries are excluded from later analysis. The code first checks whether any valid strain readings are available. If so, it calculates the mean strain by averaging all the readings. If none are available, it sets the average to none to show that no valid average can be computed. The program prints a brief summary of the processed data, including the column header, the number of valid rows, and how many rows were skipped because of data problems. It also shows the first valid strain value as a quick integrity check, then reports the average strain rounded to 2 decimal places. Together, these results give a concise view of data quality and key statistics. This script reads engineering data from a CSV file containing time, strain, and temperature values. It skips headers, blank lines, and invalid records, then stores only valid numerical entries. After processing, it reports the number of valid and skipped rows, the first valid strain value, and the average strain rounded to 2 decimal places. This ensures the analysis is based only on clean data. CSV data. CSV-style data is common in engineering because it is simple and works well with text editors and spreadsheets. Each line usually represents one observation or test case, with fields separated by commas, tabs, spaces, or another delimiter. To read the data correctly, you must treat the file as plain text and understand its structure so each field is interpreted accurately. When working with CSV files, first check the opening lines because they may contain headers or metadata, such as column names, units, or calibration details. Your program should skip, store, or use this information to label the data correctly. For the actual data rows, split each line by the delimiter and convert text fields into the proper data types so calculations and simulations use accurate numerical values. CSV files are simple in form, but real data often contains blank values, extra spaces, inconsistent number formats, or malformed rows. Large files should be processed efficiently, and each row should be checked for the right number of fields, valid numeric values, and missing data. Careful handling turns raw text into reliable information for engineering analysis and decisions. Python code, CSV data. Create a small engineering CSV file, read its rows using built-in file handling, and convert the text fields into useful numeric values for further work. This line means the script only uses Python's built-in features and does not need any extra packages installed. As a result, the code is easier to run and more accessible for users without specialized libraries. The script begins with a list of strings that represents the lines of a CSV file. The first line provides the column names for time, temperature, and pressure, while the remaining lines contain the corresponding numeric data as text. One row is deliberately incorrect to demonstrate how the script can later handle real-world data problems. The snippet represents CSV-style sensor readings stored as lines of text. Each row contains time, temperature, and pressure values, with one row intentionally missing the temperature. This small dataset simulates reading from a CSV file and helps test how data processing handles missing values. The code stores the CSV output file name, sensorreadings.csv, in a variable. Using a clear, concise name makes the data file easier to organize and access later in the script. A file is opened for writing with the selected name and UTF-8 encoding, so characters are handled correctly. The CSV lines are joined with new line characters and written into the file, creating the sample CSV for later data processing. Set up two lists to organize the data, one for valid rows with complete, correctly formatted records, and one for skipped rows that should be ignored because they are missing data or contain errors. Keeping these rows separate makes later data management and analysis easier. The file sensorreadings.csv is open for reading with UTF-8 encoding, so its contents, including special characters, can be handled correctly. The first line is then read as the header row, cleaned of extra whitespace, and split by commas to identify the column names for the data that follows. The code reads the file line by line, skipping the header and processing each remaining row. It removes extra whitespace, separates the row into fields using commas, and tracks line numbers to support error handling and report any skipped rows. The code first checks whether each line has the same number of fields as the header. If a line does not match the expected format, it records that row as skipped and moves on. This prevents malformed data from causing errors during later processing. The code safely converts three text values into numbers inside a try block. It reads the values as time in seconds, temperature in Celsius, and pressure in kilopascals. Using the try block helps handle invalid input, such as missing or non-numeric data, without immediately breaking the program. If a value error occurs while converting text fields into numbers, the code records the row as skipped and moves on to the next line. This prevents invalid rows from being processed further, while allowing the rest of the file to continue normally. The code stores each valid data point by adding the current time, temperature, and pressure as one structured record. This keeps only successfully parsed and converted values, making the data easier to use in later analysis. From the valid rows, we collect the temperature and pressure values by taking the appropriate entries from each row. These extracted lists can then be used for later analysis, such as finding average temperature or pressure. Average temperature and pressure are found by adding the valid values for each measurement and dividing by the number of entries. These means give a simple summary of the data and help show the overall trends in the valid observations. The program prints a concise summary of the CSV processing results. It shows the detected column headers, the number of valid rows processed, and any skipped row numbers. It also reports the average temperature and pressure, each rounded to 2 decimal places, giving a quick view of data quality and key statistics. This script demonstrates basic Python file handling and error checking by creating a CSV file of sensor data, including one flawed row, then reading and validating it. It skips rows with missing or invalid values, converts valid text fields into numbers, and calculates the average temperature and pressure. The final report shows the headers, the number of valid rows, skipped row numbers, and the computed averages. Writing reports. Text report formatting. Text report formatting turns raw calculation results into a clear, readable summary that can be understood without the original program. In engineering and science, it adds context, labels, and units to results, so they are complete and easy to scan. Its main purpose is to prevent misunderstandings, such as unit confusion, not to decorate the output. Begin a text report with essential context, such as the project name, test case, and date, so the file is easy to identify and compare later. Use clear labels, consistent spacing, and include units with every value to prevent misunderstandings, such as confusing newtons with pounds force. This makes the report easier to communicate, verify, and check for relevance and accuracy. Good text reports balance precision with clarity. Use only as many decimal places as the data requires, so you avoid false accuracy without hiding important differences. Keep units, number formats, and currency styles consistent, and use clear titles and spacing to make the report professional and easy to use for decisions and collaboration. Python code, text report formatting. Create a concise engineering report that presents labels, units, and numbers clearly and consistently. Then write the report to a small file and preview it to confirm the output is correct. The report is set up for a beam deflection check using 4 key values: a project label, a beam span of 2.4 meters, an applied load of 850 newtons, and a maximum deflection of 3.2764 millimeters. Together, these inputs define the basic data needed for the engineering report. The process creates a clearly named beam deflection report, then checks whether the beam stays within the allowable deflection limit. The allowable deflection is based on the span, and the safety factor is found by comparing that limit with the maximum observed deflection. If the safety factor is at least 1, the beam passes. The report is built by collecting formatted lines of text in order. It begins with a beam deflection title and a visual separator, then adds the project name and the beam span, with the span shown to 2 decimal places. This creates a clear, organized structure for the engineering report. The code adds key engineering results to a report in a clear, formatted way. It includes the applied load, maximum deflection, allowable deflection, and safety factor, with appropriate rounding for readability. This makes the report concise, precise, and easy to compare against design limits. The code adds a brief interpretation section to the report. It separates it from the previous content, states whether the deflection check passed or failed, and notes that the reported values are rounded for clarity. The program safely writes a report to a file by opening it for writing with UTF-8 encoding and saving the report text with proper line breaks. This happens inside error handling, so that file system problems do not crash the program unexpectedly. If writing fails, it catches the operating system error and prints a clear message with the details. To preview a saved report, the file is opened with UTF-8 encoding, so special characters are handled correctly. The content is read and split into lines, and only the first 10 lines are selected for display. This gives a quick view of the report's beginning while avoiding unnecessary processing for large files. The code announces that a preview of the saved report is about to be shown, then displays the report's first few lines in a readable format. This lets the user quickly check the saved content without opening the file separately. This script creates a concise beam deflection report. It calculates the allowable deflection from the span, divided by 360, compares it with the maximum deflection to find a safety factor, and marks the result as pass when the factor is at least 1. The report records the key project data, deflection values, and safety factor with units, writes them to a text file, handles write errors, and prints a short preview for review. Formatted file output. When writing results to a file, present them as a clear report rather than a list of raw values. Include enough context, such as a title, date, labels, units, and a summary of key findings, so the meaning of each result is obvious. For a beam deflection analysis, for example, the file should state the maximum deflection, where it occurs, its units, and whether it meets the required limits. This makes the output easier to review and use in later work. When writing numbers to a file, formatting should make the output clear, consistent, and easy to read. Rounding remove unnecessary digits while keeping the needed precision for each type of value. Using fixed decimal places and clear units helps readers compare results quickly and supports professional technical communication. When formatting file output, design it for its intended readers and later use. Human readers need clear labels and spacing, while programs need consistent structure, and many reports must support both. Include enough context so the results remain understandable after the program ends. Good formatting improves clarity, reduces confusion, and makes results easier to check and reuse. Python code, formatted file output. This example shows how to produce formatted engineering reports that are easy to review. Clear labels help readers understand reported values, while defensive checks help prevent invalid calculations. The pump test dataset includes 3 operating points with flow rates of 8, 10, and 12 liters per second. Each flow rate has a matching pressure of 180, 210, and 225 kilopascals, and a power use of 2.1, 2.85, and 3.45 kilowatts. These values provide the basis for calculating pump efficiency and creating a performance report. The code first verifies that the flow, pressure, and power data all contain the same number of entries, so each measurement lines up correctly. If they match, it stores that count for later processing. If not, it raises an error to stop the calculation, preventing unreliable results from inconsistent input data. The script sets up key values for pump performance analysis. It defines the water density as a typical 1,000 kilograms per cubic meter, chooses a text report file for the output, and creates an empty collection to store pump efficiency results for later comparison. The process handles matching flow, pressure, and power values together for each operating point. It calculates hydraulic power by multiplying flow by pressure and dividing by 1,000 to keep the units consistent. Efficiency is then found by comparing that hydraulic power with the actual power consumed, and each result is stored for later analysis. To find the best operating point, identify the data index where efficiency is highest. Then use that same index to retrieve the maximum efficiency and the matching flow rate. This gives the flow rate that produces the best efficiency. The code creates a new report file using UTF-8 encoding, then writes a short title for a pump performance summary. It also adds the project name, training example, to give the report basic context. The code adds clear column labels to the report for flow, pressure, power, and efficiency. It also includes the units, using liters per second, kilopascals, kilowatts, and percent, so readers can interpret each value correctly. The loop pairs each flow, pressure, power, and efficiency value, then writes one formatted line to the report for each set. The numeric values are shown to one decimal place, and efficiency is converted to a percentage. This keeps the output consistent, aligned, and easy to read. The code adds a key results section to the report, highlighting the most important findings from the analysis. It records the best efficiency as a percentage and includes the best flow rate in a clear professional format. Open the report file in read mode with UTF-8 encoding so its characters are handled correctly. Then read all lines into a list and keep only the first 8 lines. This creates a short preview, making it easy to check the report output without reading the whole file. The code confirms that the report file was created and tells the user where it was saved. It then announces a short preview and displays the first few lines of the report as one compact block of text. This lets the user quickly verify the report's contents without opening the file. The script creates a clear engineering report for a pump test by first checking that the flow, pressure, and power data all have matching lengths. It then calculates efficiency at each operating point, finds the best efficiency and its flow rate, and writes the results to a readable text file with a summary table. Finally, it prints a short preview in the console to confirm the report was created and to give a quick view of the data. Report formatting. Report formatting turns raw calculation results into a clear, reliable document. In engineering and science, results need context, organization, units, and assumptions so readers can understand what the numbers mean. A strong report includes basic details such as the title, project name, and date, then presents the data in a logical way. This makes the report a useful analysis record rather than a simple list of values. Well-formatted reports use consistent spacing, labels, precision, and units, so results are easy to read and compare. Each line should have a clear purpose, with related values aligned and clearly labeled to avoid confusion. Numeric values should include units and use enough decimal places to show meaningful differences without implying false accuracy or cluttering the report. When creating a report, plan for how it will be read, stored, or reused later. Keep it clear and consistent, with simple sections for inputs, results, and conclusions. Emphasize important outcomes, such as design tolerances, and avoid extra decoration that makes the file harder to use. A well-structured report improves communication and supports better decisions from the data. Python code. Report formatting. Engineering reports should be formatted for clear, readable output. Include meaningful labels, units, and appropriate precision, so results are easy to interpret. When creating a small report file, write it safely to protect the data and ensure reliable output. The script imports tools for working with file paths and dates. The path handling class makes file locations easier to manage across different operating systems, while the date class is used to create the current date in a standard format for the report. The script stores beam calculation results in a list where each entry includes the beam name, maximum deflection, allowed limit, and status. Beam B1 is within the 5 mm limit and passes, while beam B2 slightly exceeds the limit and is marked for review. This setup makes the results easy to process and format into a report later. The code creates a file path for a beam deflection report using Python's path handling tools. This makes the file location more reliable across different operating systems and prepares it to be used later when writing the report to a text file. The report begins by setting up its basic header information, It creates a text collection for the report, adds a clear title for the beam deflection check, includes the current date in a standard format, and states that deflection values are measured in millimeters. These opening lines establish the report's purpose, timing, and measurement context. To create a clear table header in the report, add a blank line for separation, then include column labels for the beam, maximum deflection, limit, and status. A second header line gives the related units and decision label, helping the columns stay aligned and easy to read. The code processes each beam result by extracting the beam identifier, maximum deflection, limit, and status. It formats these values into a neatly aligned report line, with numeric values shown to 2 decimal places. Each formatted line is then added to the report content. The report counts how many beams need review by checking for any result whose status is not pass. It then adds spacing for readability and includes a summary line with that count. This gives readers a quick view of how many beams require further attention. The code safely writes a report to a file by combining the report lines, encoding the text in UTF-8, and saving it to the chosen location. If a system error occurs, it prints a failure message with the error details. Otherwise, it confirms the file was written successfully. It then reads the file back and prints its contents to verify the result. The script creates a concise engineering report for beam deflection checks. It records each beam's deflection, allowable limit, and review status, then formats the results into a clear table with a dated header and millimeter units. It also summarizes how many beams need review. Finally, it tries to save the report to a text file and either prints the completed report or displays an error if the file cannot be written. Error handling. Exception basics. Exceptions are runtime errors that interrupt normal program execution, often caused by real-world inputs such as missing files or incorrect data formats. They show that even syntactically correct code can fail in certain situations. Understanding exceptions as a normal part of working with external data is essential for writing robust programs. Exceptions help programs handle problems in a structured way instead of stopping abruptly or showing unclear errors. They signal issues such as a missing file or data in the wrong format, and let the program move control to code that can respond appropriately. In this way, exceptions separate detecting an error from deciding how the program should recover or guide the user. Exception handling should match the severity of the problem. Recoverable issues can be managed with a clear response, while serious errors may require the program to stop safely. Good technical software separates manageable risks from failures that could make results unreliable, keeping errors visible and supporting sound engineering decisions. Python code. Exception basics. Exceptions help programs respond to runtime problems, especially when engineering files contain unexpected values. Defensive checks make calculations more reliable and help keep results trustworthy. We first set a file path for a small CSV data file called beamreadings.csv. This gives the script a clear location to use later when saving or loading the data. The example creates sample CSV-style data with a header for span in meters and load in newtons. It includes one valid row, one row with a zero span to test division by zero handling, and one row with a non-numeric span to test invalid data handling. This setup lets the program demonstrate how it processes both correct and faulty entries. To create sample data, open the chosen file in write mode with UTF-8 encoding, which creates a new file or replaces an existing one. Then use the WriteLines method to add the list of text rows to the file. Using a context manager ensures the file closes properly afterward, helping protect resources and preserve the written data. Set up one list to store valid stress results and another to record errors. Each valid result comes from dividing the load by the span, while errors capture problems like bad data formats or division by zero. Keeping these separate makes it easier to organize successful calculations and report issues clearly. The program tries to open a specified file safely, using error handling in case something goes wrong. It reads the file as UTF-8 text and loads all lines into a list, so each line can be processed separately later. This code handles the case where a program tries to open a file that does not exist. When a missing file error is caught, it records a clear message in the error list with the missing file's name. This makes it easier to diagnose file-related problems. After confirming that data exists, the code processes each row starting after the header line. It splits each row by commas, so the span and load values can be separated, checked, and prepared for later processing. The code verifies that each row has exactly 2 columns. If a row has the wrong number, it records an error with the row number and then skips the rest of that row, moving on to the next one. This section converts text values into numbers so they can be used in later calculations. It changes the span and load entries into floating point values inside an error handling block. If a value cannot be converted, the resulting error is handled elsewhere, so the program can continue running smoothly. This code handles errors that can occur when converting text values into numbers. If a row contains a value that is not numeric, the program records an error message and skips the rest of that row. This prevents the program from crashing and lets it continue processing the remaining rows. Before calculating, the code checks whether the span is 0 to avoid a division error. If it is 0, it records an error for that row and skips to the next one. This prevents invalid data from being used and helps keep the calculations reliable. For each valid data row, the load is divided by the span to calculate a load per span value. Each result is stored in a collection, so the values can be analyzed or reported later. The program creates a UTF-8 text report summarizing error handling results. It writes a clear title, then records how many calculations were valid and how many issues occurred during processing. This provides a compact overview of the program's execution outcome. The code ends by reporting the results of the exception handling demonstration. It confirms completion, shows the valid load values that were calculated successfully, lists any issues that were caught and handled, and tells the user where the error handling report was saved. This Python script shows basic exception handling while processing beam readings from a small CSV file. It handles problems such as missing files, wrong column counts, non-numeric data, and division by zero, while saving valid load-to-span ratios. After processing, it reports how many calculations succeeded, lists any errors, and saves the results to a text file for review. Exception handling. Exception handling helps a program deal with problems that may occur while it runs. These problems often come from outside the calculation itself, such as missing files or invalid user input. Instead of crashing with unclear messages, a program can recognize the issue, explain it clearly, and either recover or stop safely. Exception handling separates a program into a normal path and a recovery path. The normal path runs when everything works as expected, while the recovery path handles problems such as missing files or invalid data. This separation keeps programs clearer and makes it easier to apply the right response, such as asking the user to check a file or logging an error and continuing. Effective exception handling should respond to the specific problem, not treat every error the same. Missing files, permission failures, and invalid data may require different actions depending on the situation. Ignoring errors can produce misleading results, so programs should report problems clearly and handle them in ways that keep the output reliable and informative. Python code, exception handling. This lesson demonstrates how to handle errors when working with engineering files in Colab. You will create small files for testing and learn how to report problems clearly without letting the program stop abruptly. The script begins by importing tools for working with files and data. The path class from pathlib helps manage file paths. The CSV module supports reading and writing tabular data, and the statistics module provides basic calculations such as averages and medians. Together, these imports prepare the script for file handling, data parsing, and statistical analysis. The script uses the pathlib path class to define the main files it will work with. One path points to the expected censored data file. Another represents a possibly missing input file for testing. And a third identifies where the temperature report will be saved. Defining these paths up front keeps file handling organized throughout the script. A small sensor-reading CSV file is created to demonstrate data handling with possible errors. It includes time in seconds and temperature in Celsius, with several valid temperature readings and one intentionally invalid entry. This setup shows how the code reads the file and deals with bad data during processing. The read temperatures function takes a file path and prepares to process a CSV file. It creates one list to store valid temperature values and another to record any skipped rows, supporting both data extraction and basic error tracking. The program opens the specified file in a protected block so file errors can be handled safely. It reads the file as UTF-8 text and uses a dictionary-based CSV reader, so each row is treated as a dictionary keyed by the column headers. This makes the data easy to access by column name for later processing. The program first checks that the CSV header includes the expected temperature column. If it is missing, it raises an error to signal that the file format is not valid. This prevents the program from continuing with the wrong data structure and causing later errors. The code skips the CSV header and reads each remaining row. It tries to convert the temperature entry into a decimal number, then stores it if the conversion succeeds. This keeps only valid numeric temperature readings, while invalid values are handled separately. This code handles failed temperature conversions from the CSV file without stopping the whole process. When a value cannot be converted to a number, it records the row number in a skipped rows list. This makes it possible to continue processing and report the problem rows later. This code handles the case where a file cannot be found. When that error occurs, it prints a clear message with the missing file path, then returns 2 empty lists. This lets the function stop safely without crashing the rest of the program. This code handles a permission error, which happens when the program cannot access a file because it lacks the required permissions. When the error occurs, it reports that access was denied for the file and returns 2 empty lists. This keeps the function's output consistent and lets the program continue without crashing. This code handles a value error that occurs when the file data is in the wrong format, such as text appearing where a number is expected. It reports the problem to the user with the error details. Then it returns 2 empty lists to show that no valid data could be processed. The function returns both the temperatures it successfully reads and converts, and the row numbers it skips because of conversion errors. This lets the calling code use the valid data while still tracking which rows caused problems. The code tests how the temperature reading function handles a missing file. When given a path that does not exist, it catches the FileNotFoundError and returns empty results instead of crashing. The printed message confirms that 0 temperature values were read, showing that the failure is handled safely. Next, the program reads a data file that may contain errors. The temperature reading function opens and parses the file, collecting valid temperature values while skipping rows it cannot process. It returns both the valid readings and the row numbers of skipped entries, so later processing can use the clean data and track where problems occurred. The code first checks whether the temperature list is empty. If there are no valid values, it prints a message instead of continuing. This defensive check prevents calculations on missing data, which could cause errors or misleading results. This section summarizes valid temperature readings by calculating the average and identifying the highest value. These two measures provide a quick overview of the data for reporting. The report is written to a file using the pathObject's writeText method with UTF-8 encoding. It summarizes the number of valid readings, skipped rows, and the average and maximum temperatures rounded to 2 decimal places. The write operation is placed in a try block, so file-related errors, such as permission or storage problems, can be caught. This code handles operating system errors that may occur while saving a report. If saving fails because of a file system issue, it catches the error and prints a message explaining that the report could not be saved, along with the specific error details. In the else block, the program reports how many valid temperature readings were processed, identifies any rows skipped during parsing, and confirms where the saved report can be found. This gives the user a clear summary of what was completed and any data issues encountered. This script shows how to handle errors while working with temperature data in a CSV file. It creates a sample file with one intentional problem, then reads the data while handling missing files, permission issues, and formatting errors without crashing. Valid readings are used to calculate the average and maximum temperatures, while bad rows are skipped. Finally, the script writes a report and confirms the results, or reports any error if the report cannot be saved. Defensive error checks. Defensive error checks help prevent failures by verifying likely problem areas before processing begins. With files, this can include checking that the path is valid, the extension is appropriate, and each data line contains the expected fields. By treating files and user input as possibly flawed, these checks make programs more reliable and safer to run. Defensive checks help catch problems that may not cause immediate failures but can still produce misleading results. Missing labels, swapped columns, blank fields, or invalid values can let a process continue with wrong assumptions. A robust design verifies that files exist, sections are complete, numbers are valid, and values are within expected limits. This leads to clearer error messages and prevents confusing failures later. Use defensive error checks thoughtfully. Too few can make programs unreliable, while too many can make them hard to read. Check the most important assumptions, such as whether inputs, data structures, values, and outputs are valid and safe. This is especially important in professional settings where files change often, because good checks protect analysis quality and help users fix problems. Python code. Defensive error checks. Defensive checks help prevent confusing file errors, even when working with small data files. Clear error messages make it easier for engineers to identify and fix problems in their inputs. We create a small set of sample CSV lines to represent a file with a header and several data rows. The columns are time, temperature, pressure, and flow. One row deliberately has a missing temperature value, so the setup can test how the code handles incomplete or invalid data. The CSV data has 3 measurement rows. The first row is valid, but the second is rejected because the temperature value is missing. The third is also rejected because it contains a negative flow value, which is not physically reasonable. The code stores the location and name of a comma-separated engineering data file, so the program knows where to read or write it. A clear file name also helps show the file's purpose. A file is opened for writing with UTF-8 encoding, so characters are handled correctly. The example lines are joined with new line characters and written out as a small CSV file. This sample data includes a row with missing values, which can be used later for error checking and validation. The code first validates the file path by checking that it is not empty and refers to a CSV file. If the path is invalid, it raises a clear value error instead of trying to open the wrong kind of file. This defensive check catches problems early and helps ensure later file operations run on a valid CSV file. Set up separate collections for valid and rejected rows so the data can be organized during processing. Also define that each row should contain 4 columns, allowing the structure to be checked before any further validation. The program tries to open the specified text file using UTF-8 encoding and reads its contents if successful. If the file is missing, it catches the error, uses an empty set of lines instead, and records a message that the file was not found. This lets the program continue running while still reporting the problem. The code first checks that the file contains a header and at least 1 data row. If not, it records a rejection message and stops processing the incomplete file. When enough lines are present, it reads the first line as the header, trims extra white space, and splits it into column names for later validation and data processing. First, the file is checked to make sure it includes a header and at least 1 data row. The header is then split into fields and compared with the expected column count, which is 4. If the count does not match, the row is rejected with a message about the incorrect header column count, preventing processing of data with an unexpected structure. After confirming the file structure is valid, processing begins with the second line of data. Each line is tracked with its row number so errors can be reported accurately. The line is then cleaned of extra white space and split by commas into separate fields for validation and processing. The code validates each data row by checking that it has the expected number of fields and no empty values. If a row is incomplete or has missing data, it records a rejection message identifying the problem. It then skips the rest of the processing for that row and moves on to the next one. The code tries to convert each value in the current row into a floating point number for time, temperature, pressure, and flow. If any value is not numeric, the conversion fails, the row is recorded as rejected, and the loop moves on without processing that row further. The code checks whether the flow value is negative, since that would not be physically valid. If so, it records the row as rejected with a message identifying the problem, then skips the rest of that row and continues with the next one. This step stores each valid row of engineering measurements for later use. It saves the time, temperature, pressure, and flow values as floating point numbers, ensuring that only clean and reasonable data is used for analysis, averages, or reports. The code first checks whether any valid rows are available. If so, it computes the average temperature by adding their temperature values and dividing by the number of valid rows. If no valid rows exist, it leaves the average as none to show that there is no valid data to use. The report begins with a defensive file check header, then summarizes how many rows were accepted and how many were rejected. It calculates the average temperature from the accepted rows when any exist. Otherwise, it leaves the average empty. Finally, it reports the first rejected row as the first issue, or states that no issues were found. This script shows how to handle CSV data defensively by checking for missing files, incomplete rows, non-numeric values, and invalid data such as negative flow rates. It rejects bad rows, keeps valid ones, and calculates the average temperature only from reliable data. The final report summarizes valid and rejected rows, the average temperature, and the first problem found, supporting robust data handling and clear error reporting in engineering work. In this lecture, you learned to read text and CSV-style engineering data files using built-in file handling, write calculation results and simple reports to text files with clear formatting, and handle common runtime errors using exceptions and defensive checks. In the next module, Module 4, we will go over numerical methods. Thank you for your attention. See you all in the next lecture.